This is the lecturette for section 15.3, the first of two sections where we learn how to use equilibrium constant and equilibrium expressions in calculations. And we're going to look at three things here. First, how does one determine an equilibrium constant? And you do that using experimental data. And then the second is, how do you determine, if you know the concentrations of species in a system, how do you determine if it's at equilibrium or not, and what will happen if it's not at equilibrium? And then finally, the third part will be calculating what the equilibrium concentrations will be if a system that's not at equilibrium goes to equilibrium. So let's start with the first one. Let's determine how, let's see how we determine an equilibrium constant using experimental information. And the general pathway to do this is, the first thing you do is you write the equilibrium constant expression from the reaction equation. Then you measure one or more of the concentrations of species in solution once the system is at equilibrium. And if needed, you use stoichiometry to determine all of the concentrations at equilibrium, and then you just insert those equilibrium values into the equilibrium constant expression and calculate the K value. So let's look at two examples of this. The first one, a simple example where we know all of the concentrations, and then later on we'll do a more complicated one. We have this equilibrium. Two sulfur trioxides react at equilibrium to make two sulfur dioxides and an oxygen molecule. And these are the species that are found to exist in an equilibrium mixture. We want to know what is the equilibrium constant. So the first step is to write the equilibrium expression, KEQ, that's the equilibrium constant. It's going to equal the concentrations of the products raised to their stoichiometric powers. So it's SO2 squared, concentration squared, over the oxygen concentration raised to the first power, because there's just a 1 there, over the reactant concentrations, the SO3 concentration squared. And because we know all these numbers, all these concentrations, we just plug those in. So it's going to be 0.0247. I'm going to leave off units because we don't actually include units in equilibrium expressions, just by convention. And so the SO2 concentration, because there's two of them, that's squared, times the O2 concentration, 0.0330, divided by the concentration of the SO3 squared, 0.152 squared. And then we just do that with our calculator and determine the equilibrium constant. And that comes out to 8.71 times 10 to the minus 4. Okay, now let's look at a slightly harder example. And this is one that's going to introduce us to one of the most important tools that we can use when looking at equilibrium systems, and that's called an ICE table. An ICE table stands for a table that shows the initial concentrations of species before they come to equilibrium, the change in concentrations as they go to equilibrium, and what the equilibrium concentrations are. And so in this particular example, we look at the reaction where nitrogen and hydrogen form ammonia by that balanced equation. And what we say is that the initial concentrations of N2, the initial concentration of N2 is 0.1 molar, and the initial concentration of H2 is 0.22 molar. What will, and we also know that after the system reaches equilibrium, the nitrogen concentration, that started at 0.1, is now dropped to that. And so the key is, what we want to do is we want to fill out this table with all the numbers that we can. And in fact, in this case, we can fill out all the numbers. So our initial concentration of nitrogen is 0.1000. Our initial concentration of hydrogen is 0.2200. Our initial concentration of ammonia is 0. We also know that at equilibrium, the final concentration of nitrogen is 0.0271. So from that, we can determine the change in the concentration of nitrogen, because we know how much it changed by. So we subtract 0.0271 from 0.1, and that gives us a change of minus 0.0729. Now, because one nitrogen goes to react with 3 hydrogens, we know that the amount of hydrogen reacting is 3 times that. So we multiply this number by 3, so that's going to be minus 3 times 0.0729. That's the change in that. And that equals minus 0.2187. And so our final concentration of hydrogen, therefore, is 0.2200 minus 0.2187, and that comes out to 0.0013. So that's the final constant, the equilibrium concentration of H2. Now we also know that 1 mole of nitrogen reacting creates 2 moles of ammonia. So our change in ammonia is going to be 2 times 0, and it's going to be a plus because we're making ammonia, 0.0729, and that gives us a concentration of ammonia at equilibrium of 0.1458. So now we know our equilibrium concentrations of all 3 species, and we're back to where we were at the beginning of the last problem. So let's go ahead then and write our equilibrium expression K. It's going to equal the concentration of NH3 squared over the concentration of N2 times concentration of H2 cubed. And we put on our values for that. That's going to be 0.1458 squared divided by 0.0271, that's our nitrogen concentration, times 0.0013, that's our hydrogen concentration, cubed. And when we multiply that all out, we get 3.6 times 10 to the 8th. And so that's our equilibrium constant for that species, for that reaction. Now we're going to turn to determining if a system is at equilibrium. And to do that, we're going to introduce a new term called the reaction quotient, which is given the letter capital Q. Capital Q is like K. K and Q are similar to each other, except Q uses the equilibrium concentrations, the concentrations of things, whether they're at equilibrium or not. So if we have a system and we know the concentrations, we put those concentrations into the equilibrium expression. The number you calculate is equal to Q, the reaction quotient. If Q is equal to K, that means the system's at equilibrium. If Q is greater than K, remember K is basically a function of products concentrations over reactant concentrations. And so if Q is bigger than K, that means this value is, this ratio is too large, which means you have too many products. And so what will happen is products will react to make reactants. So we'll decrease the product concentration, increase the reactant concentration until we reach K. If Q is less than K, it means that this is too small, in which case you need to have more products and less reactants, so reactants will go to make products. And so that's the way you know which direction it goes. The way we talk about this is because we have reactants in equilibrium going to make products, and we always write the reactants on the left and the products on the right. If Q is too big, we know we want to make more reactants and less products, so we say that the equilibrium shifts to the left. If Q is too small, we want to make more products. In that case, we say the equilibrium shifts to the right. And we'll be using those terms, shifting left and right, throughout all of our study of equilibrium systems. So let's look at an example of this. We have the following system, and we know these concentrations, we know the balanced equation, and we know the value of the equilibrium constant. And what we want to know is the system at equilibrium or not? And if not, in which direction will it go to reach equilibrium? So what we do is we write the equilibrium expression, but we do it in terms of Q now. So Q is going to equal the concentration of ClF squared divided by the concentration of Cl2 divided by the concentration of F2. And what we do is we just put our values in for that. So ClF is 0.120, and that will be squared, divided by the concentration of Cl2, 0.300, times concentration of F2, which is 0.620. So we've just put these numbers into that equation. And we do that out, and we come up with 0.0774. And now what we do is we compare that. So Q equals 0.0774. K is equal to 22.3. And that was just a known property of this system. And so therefore Q is less than K. And therefore we have not enough products. Q is too small, so this part is too small, that part is too big. So therefore reactants go to make more products. And the reaction, or the system, let us say, shifts to the right. Now let's go to the next step and talk about, if we know a system's not at equilibrium, we know what the reaction quotient is, we know which direction the reaction is going to go, what will those concentrations be once it reaches equilibrium? How can we know that without actually doing the experiment, just by doing a calculation? And so the process here is to do what we just did. You write the equilibrium expression, you determine Q, you see which way it's going to go. Then you set up an ICE table and you determine the equilibrium concentrations in terms of how much is going to react. And how much is going to react is going to be called X. That's the amount reacting. And then we'll insert those values into the equilibrium constant expression and solve for X. Once we know X, we'll use X to determine the initial concentrations. We use X and the initial concentration to determine the equilibrium concentrations. So let's look at an example of that. So we have an equilibrium system here. We have two versions of the two isomers of the molecule butane, or of the molecule with 4 carbons and 10 hydrogens. This is butane, this is isobutane. And they're in equilibrium, and at a particular temperature, the equilibrium constant is 2.5. If we have a flask that initially contains 0.200 molar butane, what will the concentrations be if equilibrium is reached? And so that means we're starting with just this. Some of this is going to go to react there. And we're going to do that until this ratio is 2.5. So in this case, we don't actually even need to calculate Q, because we know there's no isobutane. So the reaction's got to go to the right. So we know the reaction is going to go to the right. So we know our initial concentration of butane is 0.200, and we know our initial concentration of isobutane is 0. And we know the reaction is going to go to the right, so we're going to lose butane. And here's the idea with this X. X equals the change in the butane concentration, or the absolute value of that. So butane decreases by X, and isobutane increases by X. And therefore, at equilibrium, butane will be 0.200 minus X, and isobutane will be X. And so then we know, in terms of our initial concentrations and X, what our equilibrium concentrations are. I'm going to go to a new slide here and repeat that. And so we know our initial concentrations and our final concentrations are this. And now we insert these into the equilibrium expression. So K equals, I'll do this over here, K equals the isobutane concentration over the butane concentration. And that equals 2.5, which equals the isobutane concentration, which is X, over the butane concentration, which is 0.200 minus X. And the key is we can now solve for X. That is, we're going to solve for how much actually reacted. And when we do that, we see that 2.5 times 0.200 minus X equals X. Therefore, 2.5 times 0.2. 0.5 minus 2.5x equals X. So therefore 0.5 equals 3.5x. And therefore X equals 0.5 divided by 3.5, which equals 0.143. So therefore, the concentration of isobutane at equilibrium is equal to 0.143 molar, because it's equal to X. Concentration of butane at equilibrium is going to equal 0.200 minus 0.143, So that's going to equal 0.057 molar at equilibrium. So we found our two equilibrium concentrations. Let's do our final check and just plug them into the equilibrium expression to make sure that we get the equilibrium constant. So if we do that, our isobutane concentration is 0.143. Our butane concentration is 0.057. And if we divide that out, we actually get 2.5, which is a good check that our equilibrium concentrations are correct. And that's the way that works. We'll be using this throughout the next four chapters.